So let's see, how's it going? We got questions? I got answers. You want to go first?
Yes. The section 2, you got add the GRE verbal and font inside it. No, the section 3. Yes, and then for the question sorry, let me see. Question 20, you asked for the, yeah. The change for the variables.
After adding GRE scores, enter the change in the proportion of variance accounted for due to the scores. So there's an R-square from this model. I want you to compare it to the one from the previous model and take the difference.
Yes.
You mean the previous model from?
Section 2. I'm sorry?
What is the test? I mean, I can subtract using the 2R-square, but
yes.
How can I get the test statistics?
Yes, that's fine.
You have, let me pull up example 6, because there's an example of that as a concept. So the very last model that has all the predictors together at the same time. So this is, let me see what page I'm on, 11, page 11 on example 6. So if you want to know whether a set of predictors has significantly increased the R-square, then you need a multivariate wald test. So the contrast is the way that you can ask for that. As an example, I have 2 here. If you were to list every slope that's in your model with a 1 behind it, separated by a comma, that is actually what this model test is giving you. So the test of the model that shows up by default is a test of everything that's in the model. So just for the purposes of demonstration, this is how I would get that test if it weren't showing up by default, which sometimes it doesn't in more advanced models. To get a subset, for example, if I want to know if dementia by itself, these 2 effects for dementia contributed to the R-square, then I ask for just those 2. So the idea for GRE scores would be to do this, to lump them together, and since they're the new thing that's in the model, they have to be responsible for that change in R-square.
So when you're saying GRE scores, you're saying by lumping them together, it would be like quant verbal.
Yeah, it'd be verbal 1, comma, quant 1 also. 1 just means it's asking you to add them together. It's because sometimes you would subtract them, like this one. What this one is doing is asking for the difference of the slopes, which is the difference that's not given directly by the model as a linear combination.
How do you know which 2 models we are contrast?
So in section 2, you're adding a single effective motivation, right? So the test of whether motivation accounts for significant variance is the same test as the motivation slope, right? It's a 1-to-1 correspondence. After you add 2 more slopes for the effect of GRE, we're asking if those 2 improve the model. And so a contrast like this is how you would find that out.
So does that mean if I put the contract, I should put it under the new model?
Yes, as part of the new model, yes, before the run.
So what if I want to add 1 more model, and I want to contrast this one to the one before, and just add a contrast of the new one?
You putting the contrast in functionally compares it to the previous one.
Okay.
So you can do it all at once.
So then in essence, so it asks for the denominator degrees of freedom and the proportion of the test statistic and stuff. So when we're adding in the contrast, in essence, we are making a new model that will have
A subset of the model.
Subset of the model.
Yeah, it's not a new model, but you're asking for the to piece it apart and ask for what is the contribution of these 2 things. The model that you get is the contribution of everything all together. So when you do a contrast,
Oh, I see, okay.
you end up with like this table right here. And so it doesn't give you denominator degrees of freedom. This is numerator degrees of freedom, which is how many things are being tested. But it's the same denominator degrees of freedom as for the model itself, which is right here. Okay. All right. Did that help? Good? Good? Okay. Other questions? So you have until Friday. The idea being that you can actually take a break if you finish this, right? You can ignore this class for like a week then. Come back. All right. I'll ask again on Thursday, office hours today, of course, if anybody wants to have any extra help. Otherwise, what were we talking about last time? Do you remember? What do you remember from last week? Feels like a long time ago, doesn't it?
Tuesday.
It's only Tuesday. What did we talk about last time? I'll take interactions. What's an interaction? Moderation. So how do you fit an interaction term in the model? Like literally, what is it? Yeah, it's a multiplicative combination of two variables. So some packages actually make you define that as a new variable in your data set. You don't have to do that for GLM, but conceptually that's what it is. It's adding another predictor into the model that is literally the multiplication of the two. What does it mean if you have an interaction? Like if you have an interaction of X and Z, what does that mean about the effect of X or the effect of Z? They're what?
Not mutually exclusive, so you would.
They keep talking. Mutually exclusive to me means that you're saying that they're unrelated.
No.
But their effects are related. So what does the interaction term do?
They're conditional.
They're conditional, right? So they take, the interaction term takes the effect of X and changes it as a function of Z. It also takes the effect of Z and changes it as a function of X. And the 4 ways it can change it? More positive, less positive, more negative, less negative. That's it. The same way that you have, those are the only 4 kinds of quadratic trends too, because a quadratic trend is a 2-way interaction. So it's the same. Yeah. So moderation is the idea that the effect of a variable depends on another variable in the model. Broadly construed. Yeah, moderation is interaction terms, which is how you test moderation, is the idea that the effect of a predictor variable depends on the value of another predictor variable. And they're conditional. So the main effects become conditional, right? They are specific to the interacting predictor being 0, which is another reason why centering is important. So we did some practice with centering and conditional effects. So we did this slide. This is slide 11 in lecture 7. If you don't center your predictors, then it's possible that your intercept and the main effects of those predictors are nonsense. They're not wrong, but they're useless because they're describing people who don't exist. So for instance, in this model, if we have GPA as the outcome, attitudes on a scale of 1 to 5 as a predictor, education in years as another predictor, given the interaction, the slope for attitudes is specifically when education equals 0, which is not likely to exist in a data set. Likewise, the slope for education is specifically when attitudes equal 0, which is impossible on a 1 to 5 scale. The interaction term takes each of its slopes for the main effects, and it makes them more positive, more negative, less negative, by each unit increase in the other variable. So if I have and effective attitudes, that's 1. That's specifically when education is 0. If I move education up 1, then the slope, beta 1, changes by 0.5. So this is still a slope, but what it operates on are the main effects, not y. So the interaction term changes the main effects as a function of the interacting predictor. Those then adjust y. Y hat. So we fixed it by looking at what it would mean for each of these coefficients if we centered at middle values that we would actually observe in a data set. So the intercept changed, beta 1 changed, beta 2 changed, and beta 3 stayed the same. The interaction is always the same if it's the highest order term in the model. And so if we take the 1 for attitudes, it would become 7 if education were 12 as the new 0 point. Because it starts at 1, 12 times 0.5 is 6, plus 1 gives me the 7. Likewise, the slope for beta 2 used to be 2. To get to what it would be if attitudes is 3, we take 3 times 0.5, that's 1.5, and add it to the 2, and that's where we got the 3.5. Now, we can't just use these coefficients as they are, right? We don't have standard errors, we don't have p-values, we don't have any of the stuff that goes with it. But we know how to get it. So estimate statements or LUNCOM. So I'm going to show you a process that's known as decomposing an interaction term. That's a bad word. It makes me think of like, you know, dead people in the ground or something. Even worse, people talk about doing this to probe an interaction term. Exactly. I don't know about you, but when I hear the word probe, I view Eric Cartman from South Park talking about Ada probes. Because that was the very first episode of South Park that I saw where he had an Ada probe. Is that decent, Cartman? I'm trying. Yeah. That's decent, Cartman? Yeah, I'm trying. So yeah, we're just going to estimate some simple slopes. We're not going to decompose or probe or anything that just sounds kind of, makes me squishy. So we did this before, but just to review how asking for predicted outcomes is different than asking for simple slopes. So if you want to generate predicted outcomes so that you can make a picture or otherwise talk about what would be expected from your model based on certain combinations of predictors, what you have to do is fill in a value for every predictor that is part of your model. So we're going to do this. So I've started you off with an intercept because at a minimum, a predicted outcome has beta 0 in it, right? That's your jumping off point. That's your reference point. When would beta 0 be the only thing we need to create a predicted outcome? Louder?
I'm so unconfident that I don't want to say it loud. And it would be predict an empty model?
Oh, I like that one. Yeah, that would be true. I didn't think of that, but you're right. But when else in this model would beta 0 be the only thing we need? When we're at the centering points, right? So if I want a predicted outcome for somebody with attitudes of 3 and education equals 12, the rest of this zeroes out if those are my predictors, and beta 0 is it. So beta 0 is my reference point. It's the you are here sign. From there, we have to adjust the prediction based on what the model says via the slopes of the predictor variables. By the way, I once had a professor say it is better to be wrong than vague. So just remember that, like, be wrong with authority. You know?
Was the quietest I've ever been.
Because wrong answers are helpful, because that gives me a chance to clear up misconceptions. I like wrong answers. So we need a 1 for the intercept. So if I wanted to generate predicted GPA for somebody with an attitude of 5 and education equals 16, what do I put here and don't say 5? I put 2, right? Because 3 is my 0. And 5 is 2 more than 3. Likewise, what do I put here? 4. And what do I put here? Yes, 8. Why 8? Because you multiply them together. That's it. Because 2 times 4 is 8. That's why. This one,
Yeah.
this is supposed to be education equals 16, and
Oh,
12
minus
is my
12.
0. So, yep. That's the tricky part about this, is trying to figure out what the centered values are, not the original. We'll do it again here. If I want, yeah, go ahead.
Would you, if this was like in our homework, would you give us what you want it to be centered? Like, we're never gonna have to figure that out, right?
Yeah, you are.
In real life?
Yes, in real life.
Okay, so then, but we would have already set up that model.
Yes.
With the centering values.
Yes,
And that's what those numbers are.
correct.
Okay.
Correct. So yeah, putting these in the equation shows you what 0 means for the predictor.
Yes.
That's the
Okay.
idea. In life, like when you don't have green boxes to rely on anymore, centering values are chosen usually for convenience. The mean of the variable is a fine choice. The minimum or the maximum, something usually towards the middle is conventional. I tend to round things because it's easier to think about like the interpretation of my intercept and my simple main effects in the presence of an interaction is talking like a particular kind of person, like an 80-year-old or somebody who has 12 pounds or whatever. So that doesn't really matter what the values are so long as they mean something to you, because then your model parameters mean something. That's why. So running descriptives on the variable would be a good place to start. And that's the reason why in all of my examples, we do that first. So, okay. So if I want, and yes, in your homework, I will always tell you what I want you to center at, because that's the only way I can ensure that my model matches yours in terms of the answers. Okay. If I wanted to generate a predicted outcome for somebody with attitudes of 1, what goes here? -2. You guys got this. 0 and why 0? Yes. Okay. Last one here. Attitude of 3, education of 20. What goes here? 0. Eight. Very good. And last but not least, 0. And you can state a few people, you would fill in the exact same things. It's just that you have the explicit addition and multiplication there. So not so bad, right? So this is how you would generate predicted outcomes for any kind of person. Do you remember the other 2 ways that I mentioned? And we'll see an example today. Excel, right? And fake people, yes. So fake people was the idea of adding people to your data set that have these prototypical values that you want predicted outcomes for, asking the program to generate predicted values for everyone in the data set, including your fake people. That is helpful to not have to write all of these individual statements, as well as if you change your model, the predictions and everything update themselves. So I will show you an example of that today. Okay, good. So when you're generating predicted outcomes, everything that's in the model goes in these statements. If you leave something out, it's as if you've set it to 0. So if that's what you want, like I don't have to type this, right? If I literally took out this line, that's what it would be doing. So I'm putting the 0 in here for pedagogical purposes, but we wouldn't need this or this in here, because it's not doing anything. It's not adding anything to the prediction. Okay. So how do we do this for the slopes? The same idea. We can ask the model to tell us what the implied slope is for attitudes and education at any level of the other variable, not just the ones that are given to us by the model directly, but any. So here's how this works. Here's my predicted equation. So this is like my y hat. It's a very long hat, more like a sombrero or a beach hat or something. So this model gives us predicted outcomes. It gives us predicted slopes for attitude at any level of education and a predicted slope for education at any level of attitude. Beta 1 happens to be the expected slope of attitudes when education is 12. Beta 2 happens to be the slope of education when attitudes is 3, but we can get any other combination that we want. And the way we do this is to identify all of the effects in the model that have to do with the slope we're interested in. For example, if I want to know what the effect of attitudes is for any kind of person, I got to figure out everywhere where attitude shows up. Right now, it's 2 places, here and here. That's step 1. Then we factor attitudes out, and the term that's left is its slope as a linear combination. And so it will look like this. So if I want to know the slope of attitudes, then that is going to be a function of the main effect, as well as the value of education that I want it for. Likewise, if I want to know the slope for education, it's going to be a function of its main effect plus whatever modifies it. If I factor out, basically like suck out the thing that's in common, that's another technical term, and stick it in the back. Normally when you factor something, you stick it in the front, but it looks more like what you're used to if you stick it in the back. You're left with these. So for the first line, if I take attitudes out of here and stick it in behind them, then this is how I get a slope of attitudes. So it's beta 1 at a minimum, right? It would stay only beta 1 if I were asking for the slope for education equals 12, because then this part drops. If I wanted the slope for education equals 13, then it's beta 1 plus beta 3. If I want the slope for education equals 14, it's beta 1 plus 2 times beta 3. If I want it for 15, beta 1 plus 3 times beta 3. So this is our new slope. It's a linear combination. Likewise, if I wanted to do the same thing for education, take education out of here and out of here, stick it behind them, this is my new linear combination. The slope of education is only beta 2 by itself if attitudes is 3, because then that drops. If attitudes is 4, it's beta 2 plus beta 3. If attitudes is 5, it's beta 2 plus 2 times beta. Right? Yeah. So we have to ask it to estimate this quantity and tell it what is the value of the interacting predictor that we want to have the slope for. And in case you care, here's how it gets the standard error. So in theory, you could calculate all of this stuff by hand, but I like you more than that. I'm not going to make you do that. Are the starbursts gone yet? No, I can't chew and talk, but you guys can. Hit me, yeah. Yeah, I passed one of the other professors in the hallway, and I commented like, well, you must be heading to class. I'm like, yeah, I'm trying to get rid of the Halloween candy. He's like, oh, you're bribing them. I said, yeah, actually, it's working really well. Quick aside, in high school, I had a math class, junior and senior year was right before lunch, and I had a teacher who handed out candy for like good homework grades and test grades and stuff. And she wasn't very diligent about keeping track of the candy, so it just kept going around the room, and I was usually starving by then, and so I just kept, punching. Went to the dentist after graduation, and I had 15 cavities.
Oh my.
I'm not even exaggerating. So part of me is like, go brush your teeth after class, okay? But enjoy the candy while you're here. I thought it might be a thing. I'm thinking about just like having candy all the time as a matter of discourse. I don't know. Would that be too over the top? No?
Maybe a little bowl.
Yeah.
Then you pass it around.
Yeah, I mean, well, a class that starts at 12:30, it's like either you had lunch early or you haven't had lunch yet, so it's kind of the same. Yeah, so sorry about that. So anywho, yeah.
I think there are studies done that say that if you have like mints, it's supposed to activate some sort of brain stuff and it's supposed to help you learn better.
Okay.
When we would give our students the ACT, we always gave them mints during the test.
Mhm.
Anything. And neoliberalism is terrible.
So I can bring mints too then. I'll just have like a buffet, right? We'll just have like little trays of different things and you can,
Chocolate, some
Yeah.
mints.
but never the two together because that is wrong.
Oh,
Chocolate and mint together is wrong. It's so gross.
Nature's wonderful
I
combination.
love mint and chocolate.
Oh, no.
Oh,
No. Anywho, I feel very strongly about this. But, all right. So let's see how to make SAS and stay to do the decomposition / probing / trying to get simple slopes of other levels of interest. Because when you want to try and explain what the interaction is doing, this is one way to do that. So here is the predicted model again. The quantity that we're looking for is the attitude slope if education equals 10. So just to go back one slide, this is what we need. Beta 1 plus beta 3 times education minus 12. Okay, so I've started you off here with zeros because this is something that people commonly screw up, and so I wanted to make sure that this is explicit as possible. The intercept does not go into a predicted slope. We are predicting a slope, not an outcome. So intercept has nothing to do with it. So what you're filling in here is different now. Because what we're trying to create is this. So when you see attitudes, it's actually asking about the slope. So this is going to be a 1. Whatever the slope is you're trying to get, it's a 1. This refers to beta 2. The main effect of education has nothing to do with attitudes. It doesn't have attitudes in it. So we don't use it. That's 0. Not here. Now this is where it gets tricky. This number right here is the value of the moderator. So you see on the previous slide, I need to put these on the same thing here, that would help. Do this here. That right there. Okay. This is the thing we're estimating. So I need 1 beta 1. I don't need any beta 2s. And how many beta 3s I need depends on what is the value of education that I'm asking for the attitude slope for. If I want it for education equals 10, then what goes here is -2. Likewise here, if I want the attitude slope at a minimum, right, I need 1 beta 1 always. That's why the 1 is here. I don't need any beta 2s. And if I want it for education equals 18, what goes here? 6. Very good. Now let me go back and get the other linear combination. Okay. Now we're going to do the same thing, but for ed. If I want the ed slope, do I need any beta 1s?
No.
So what goes here? 0. Likewise, or this one also, sorry, it went down instead of across. What goes here? 1. Because at a minimum, I need 1 beta 2 to make my slope. Now this time, we are filling in the value for what we want. The moderator is attitudes, because we're estimating the education slope. So it's always the other variable that you're filling in here. So if I want it for attitudes equals 2, what goes here? -1. You got it. Likewise, last one here. Ed 1. If I want it for attitudes equals 5, 2. So at the very beginning of this semester, I told you that statistics has very little to do with math and a whole lot to do with logic and working memory. Do you believe me now? There's very little math involved. Learning how to communicate with the program, learning all of the terms and the letters and the symbols requires working memory. So what goes after the interaction term, and this is the value of the moderator. So the first 2 lines we're filling in the value of Ed, because what we're trying to estimate is the attitude slope. And the second 2 lines, we are filling in the value of attitudes, because what we're trying to estimate is the education slope. Okay, how are we doing? Not too bad? Okay, all right, I'll work with that. All right, that is, yeah, let's go ahead and do this. Okay, a little bit left here. Regions of significance. So I am giving you arbitrary values of these things to fill in, right? If these are quantitative variables, I could ask for anything. I could ask for 10, 11, 12, I could ask for 33.5, right? It's, at some point, you want to be able to describe what happens to the slope over a range of values, not just specific points if the specific points are arbitrary. So it's different if you have quantitative variables than if you have categorical variables. So for instance, here's a different model. This is age, gender, in which 0 is the man and 1 is the woman, which is why I'm naming it like 1, like is the woman, and their interaction. So assuming that we live in a world in which gender is binary, which it is in this example for convenience, there are only 2 possible age slopes that would be of interest, right? Age by gender tells me that the age slope is going to differ between men and women. So given the coding, beta 1 is the age slope for what kind of person? So here's my coding. That's a man. The model will tell me that it differs between men and women by beta 3. To get to what it is for women, it's beta 1 plus beta 3. So if I want the age slope, I go a 1 here, meaning I need, at a minimum, I need a beta 1. If I want the age slope, do I need a beta 2? Nope. Does beta 2 have age with it? Then nope. Now, if I want it for a man, what goes here?
Zero?
Yep. If I want the age slope for a woman, what goes here? How many beta 1s do I need? 1 of those. Do I need any beta 2s? Nope. This is where people sometimes get confused because it's like, but you want it for women. So don't you need women? No, because we're asking for the age slope. The only things that take values in here are things that have age attached to them. And what goes here? 1. So if you look at what the numbers are doing, the age slope for men is not a linear combination. It's just this. It's just beta 1. The age slope for women is beta 1 plus 1 beta 3. So age slope for women, now we have all the pieces of information. I would get beta 1 directly tells me whether or not the age slope is significant for men. Beta 3 directly tells me if there is a difference in the age slope between men and women. And beta 1 plus beta 3 gives me what the age slope is for women. That's all I could want to know about the age slope from this model. Those are the only 3 things. Now, if we go the other way and we talk about gender differences and use age as the moderator. So age 85 is my reference point. So beta 2 is the gender difference for an 85-year-old. What if I wanted to get the gender difference at age 80? Okay, do I need any beta 1s? Nope. Do I need any beta 2s? I need one of those. Now, if I want the gender difference for age 80, what goes here? -5. How about the gender difference at age 90? Do I need any beta 1s? Still no. Do I need any beta 2s? Need one of those. And what goes here if I want the gender difference at age 90? +5. Got it. Yep. And each of these needs a semicolon, by the way, after that. So to be proper SAS statements. But this is arbitrary. How many possible gender differences are there implied by this model? Well, gender differences. I've asked for 2. How many could I have asked for? How many unique values of age do I have, right? Like, and intermediate values, right? It's infinite. So how do I take that into account in describing the range of when gender differences matter? Well, I can calculate regions of the moderating variable under which the difference would be significant. Regions of significant. So the idea is to turn the T formula on its head. So the T test of a slope is the estimate of the slope divided by its standard error. Another way of saying that is the square root of the variance around the slope estimate. Standard error is like standard deviation. What we can do is solve backwards to figure out the value of the slope at which T crosses the limits of significance, plus or minus 1.96. The other piece of information that you need to be able to do this is the covariance between the slopes, which is not something I think you'll ever need again, other than just to do this one trick. So I wrote a SAS macro that does these calculations. I also made an Excel spreadsheet. They're part of the example that we go with it. But here's one worked out example of the numbers so you can see how this would play out. So let's say that this is my set of results. I'm interested in the gender difference and the regions of age in which it is significant. So let's say that beta 2 was estimated as minus 0.53. That is specifically at age 85. So women are lower by about 0.5 point, and it's significant. The interaction term says what is going to happen to the gender difference in older people. Which pattern is this?
More negative.
This is a more negative. Does that mean stronger or weaker?
Weaker, going
It's going away from 0, that means stronger actually. More negative or more positive are both stronger. More anything. Because a more negative effect is a stronger effect. So what the interaction coefficient means is that for every year of age, as the moderator, this gender difference of minus 0.5 becomes more negative by 0.11. So this is operating directly on the slope. So I could figure out at what age this difference becomes non-significant. It would have to be at younger ages, right? Because if the effect is getting bigger in older people, it has to be getting weaker in younger people. So at some point, this gender difference will cross the threshold to be non-significant. I can turn the T formula around to figure out when that is. Now, well, I can do it. Someone else did all this, right? I didn't invent this. I'm not capable of this sort of sorcery. I'm very bad at rearranging equations and that kind of thing. I used to be good at it. I used to get candy for it, in fact, but it's gone because, it didn't get used. But after doing the magic calculations, it works out that the regions of significance for age as my moderator are 60 to 80, give or take. So what that means is that for any value above age 79.52, the gender effect is going to be significantly negative. So it's significant at 85. The point at which it goes from 0 to significantly negative is age 79.52.
So in other words, you're saying.
Getting pain out. Go ahead.
So the reasons of okay, so gender doesn't matter. Gender isn't significant before the age of 60 or after the age of 80 because they become more equal in regards to.
Not exactly.
Okay.
So we have a negative gender effect, which in this case means women are lower. So it's like this, okay? So this is the one that's given by the model at age 85. There. The regions of significance tell us that the gender effect is predicted to be significantly negative above age 79.5. So that would be like that, let's say. Let's say this is age 80 as the magical cutoff. So it would keep getting more and more negative, right, at older ages, right? That's what the pattern is. But it also, what happens to it as age goes down in younger people? If I were to keep drawing, right? It's because it's changing by a constant amount per year of age. It's becoming less negative by 0.11 as age goes down. And so what we want to know then is at what point does it start actually become positive? And that point was calculated to be about 60. So that's about here. So for anybody 60 and younger, the model says there is a gender difference favoring women. For anybody from 60 to 80, the gender difference is non-significant. And anybody older than 80, the gender difference favors men. So I really like this technique because it makes a lot more sense to me than just picking arbitrary ages to ask for slopes at. A common thing that people do to talk about interactions and to make these sorts of plots is to pick plus or minus 1 standard deviation of the variable. And so they might show a couple of lines in this case, but the model predicts an infinite number of lines. This slope changes its value by 0.11. It becomes more negative as age increases. It becomes less negative per year as age decreases. That's what it means. There we go. All right. How are we doing?
So the words we would
Cool.
use is gender effect, because there's not like another thing, right? So it's not like gender effects on blank.
Gender effect on whatever this y-axis is.
We don't know though what it is.
Make it up.
Okay, that's where I'm thinking.
Yeah, I got a story here. Like, it's actually from the cognition example. That's where I took those values from, is I fit a separate model just to build this. But yeah, so gender effect is not very descriptive in the sense that you have to know the direction. You could say the disadvantage for women. The disadvantage for women becomes stronger, is exacerbated by age. I like that one. I did terrible on my GRE verbal, by the way. It was back when the test was adaptive, the whole thing. And so I could tell I was doing terrible, because at some point the questions were like, black is to white. I'm like, I think I'm down in the cellar of the question. Like, nothing like realizing you're sucking to keep your performance aces. But yeah, exacerbated. So the female disadvantage is exacerbated in older age. It is amplified in older age. It is, help me out here. People who did better on the GRE than me. You think of any better words? Yeah, see, this is more negative is like the first step, right? Putting it into words that people can relate to would be next. So, I once described something in a paper as more negative, and a reviewer said, I have no idea what that means. It's more negative. Like,
What else do you want from me?
So these sorts of pictures can help in explaining what that means. Anywho. So that's it. Moderation. Now, how to get at these things differs by variable type. We're starting with quantitative because I actually think that's the easiest. We'll do interactions with categorical next in the next example. But we can do this. So let's look at an example. Let's do example 7. So the first thing that I did in example 7, so this is the same data set we were playing with before. We're predicting cognition from age, grip strength, and dementia group, as well as gender. So the setup for this is identical. I changed one small thing, by the way, in this data code. I used to gen these two contrasts to be equal to 0 to start with. I changed them to missing data because I realized that everything would be 0 if they were missing, if they didn't have a dem group. So just as a little bit of better ways of doing thing, I genned it to be missing to start with, but otherwise it's the same. So this is the model that we ended up with that doesn't have any interactions yet, but it has all the predictors. So at the beginning of this lecture, I talked about 3 different ways of getting predicted outcomes. So one was Excel. You can write the predicted outcomes yourself and make a picture yourself. 2 is this. So I asked for predicted outcomes for age 80, 85, and 90 crossed with grip strength 6, 9, and 12. Those are roughly plus or minus 1 standard deviation of each variable. This right here, ODS output, what that does is save the table of these results to a data set. So they're right here. I then went into the data set and labeled age and grip so that I could make the picture that shows up on your slide. So this right here. The fake people is the other option. So this was in the slides as well, but just to review, I'm making a new data set called fake people in the work library. The columns are going to be named on the input, person, age, grip, and then my 3 contrasts for gender and dementia group. I then asked it to create centered versions of my predictors as well. The first column is the minus 99 because that's person ID. I wanted to make sure I picked a number that was obviously fake. And also, if you sort, they're first in the data set, so that works. I entered the values of age and grip, and then it computed the centered versions for me. I merged the fake people with the real people, re-estimated the model, and added this line right here. So you've seen this once or twice before, but I didn't make much of it. What this is doing is saving a new data set, which I have named Pred Outcomes. You can name it whatever you'd like in the work library, with columns where the predicted outcome by the model is saved as y hat, and the standard error for each predicted outcome is saved as SEY hat. Those are my names. So it generates those two columns for all my real people and my fake people. So this is the easiest way to get predicted outcomes to make pictures with, because all you have to do is enter cases that have the values of the predictors, and every time you change your model, the predictions will change themselves, and you don't have to write more than just this one line to get the predictions, whereas like up here, I had to write a different line for every single point. And there's my picture. And Stata wins on this, as I mentioned. Margins is a way to ask for multiple sets of predicted values, looping across values of the predictor. And margins plot then will give you that. The only problem is that the output in Stata could not be less helpful. So you end up with this really long table telling you what these numbers correspond to, but it's not put together. So you have no idea what these predictions are. You have to go back up into the table and see what the logical order is, because 1 to 9 does not help. I just know there's 9 numbers, so. All right, and here's my picture. So this type of technique of making pictures will certainly come in handy once we have an interaction like this one. So this is straight out of chapter 2 of my book, which is the reading for this section. So I would recommend it, not just because I spent 5 years writing the book, but that chapter, I have been told, has helped a number of people try to learn interactions. So I'm kind of proud of it. But if you miss anything that I'm saying, it is all in the book. So here's my model. Here is my new interaction term. So in SAS, it's an asterisk. In Stata, it is a #/ whichever of those you want to call it. Okay. So I have a few things here related to dementia group. So dementia group is coded so that none is the reference. So one of the slopes in my model will be the difference between none and future. The other slope in my model will be the difference between none and current. If I want future versus current, I have to ask for it. And so that's what this line gives me. It's the difference of beta 5 and beta 4. I use a contrast to get the corresponding semi-partial correlation squared. And then this right here, that's another instance of me asking for a combined test of my two contrasts. It's known as an omnibus effective group in ANOVA language. It's the idea of just, I want to test for all the group differences that are implied by this variable. So it's lumping together the two contrasts to give me another F test, multivariate delta F test.
Homework, like what we have to do for.
Exactly. Just like, yep. You can lump together anything you want, but it's common when you have a grouping variable with more than 2 categories to ask for one result that sort of summarizes the whole thing. And I'm also asking for predicted outcomes from my new model. So my fake people are still in my data set here. And now the model has changed, but nothing else has to change. So the outcomes are going to be updated based on the model. Okay. With me so far? All right, now the fun part. Simple slopes. That's what they're called. I don't know where the language came from, but simple is a thing. Like it's not meant to be like, oh, this is so easy. Like it just means that it is a slope that's specifically at a value of another variable. It's conditional. So conditional might be a better word than simple, but that's the language. So if I want the simple effect of age, meaning what the model says the age slope would be for any value of the interacting predictor grip, first step, go to my equation, find all the terms that have age in them. Right now, there's only beta 1 and beta 6. Grab those. So here is how the model tells me what the effective age is going to be for any level of grip strength. If I factor age out and stick it at the end, the slope for age is given by this linear combination right here. Beta 1 plus beta 6 times grip. So I have asked for 3 example age slopes. So the variable for age, that's the slope that I want, so it gets the 1, because at a minimum I need a beta 1. How many beta 6s I need depends on what the value is for grip that I'm asking for the age slope. So I have -3 for 6, since grip is centered at 9, 0 for 9, and 3 for grip equals 12. Now, one of these is already given to me by the model. Which one? A second one, right? Because that is what beta 1 means. It's the effect of age specifically when grip equals 9. So I didn't have to write that one, but I do so for completeness. And also because it can be handy to have all your answers in one place. Likewise, if I want to know what is the grip strength slope for any age, go to my equation, pull out the terms that have grip in them, factor grip out, and the slope for grip is this linear combination that's left. So now I asked for 1 beta 2, and then the value that goes here is the value that corresponds to age as the moderator of the grip slope. So age 80, 85, and 5, and the middle one here is the one that would be already given by the model, because that is just beta 2. So now, if I wanted to write out the estimate statements to create predicted outcomes, so you can do fake people or you can write out these statements. I have intercept, and then the values that go here are the values of the predictor variable for which you want the predicted outcome. So if I want it for an 80-year-old, that's -5 for age. If I want it for grip 6, that's -3 for grip. And why is this 15 here? Yes, -5 times -3. It's positive. I mess that one up sometimes too. Now, I have in the comment that these estimates are implicitly holding sex to men and the dementia group to none. Why is that? How do I know that? Let's put it that way. Are those variables in these statements? Nope. So what value am I giving them by not including them? 0. So what does it mean to be a 0? It means you're at the reference group for gender, which is men, and the reference group for dementia, which is the none group. Now, why is that reasonable to do? If my goal is to show the effects of age and grip strength, according to the model, does the effect of sex, which is right here, differ by age or grip strength? Nope, there's nothing in the model that would make it that way. So the main effect of sex right here is marginal, is unconditional. This is the gender difference according to the model for everybody. Likewise, these effects of dementia, they're all by themselves. They don't interact with age or grip strength. So those are the dementia group differences for everybody. So by not including gender or dementia group, the y-axis is potentially higher or lower than it would be for other groups, but these slopes, age for age and grip, would be the same. Now, Stata folks, I have written out more code than you actually need. So the analog to doing simple slopes are these lincoms. They look exactly like the estimate statements in SAS, just with the addition and the multiplication. But in between them, there are special cases of margins. This does the same thing. So Stata wins again on margins. dy dx, that means derivative. So what it's doing is getting the age slope over a range of values for grip. So the first is starting at -3 in increments of 3 and stopping at 3. So it's going to do grip equals -3, 0, and 3. The opposite is done by the second statement. This is giving me the slope for grip at ages, -5, 0, and 5. So the parts that are highlighted are redundant, but I include them because it's easier to see what's actually happening. And these estimated outcomes, predicted outcomes, all of them are written by that one line. Okay. So let's see what happens. So my previous model was significant in terms of its R-square. It's 0.277. After adding in the interaction, the R-square went up to 289. Here are the results. Do I know if that difference in R-square from 0.277 to 0.289 is significant? So the previous model that only had main effects had an R-square of 0.277, and that was significantly greater than 0. My new model that added an interaction between age and grip has an R-square of 0.289. Do I know from anything that's up here right now whether that change in R-square is significant? Yeah? Terry thinks so. What are you staring at, Terry?
For age times grip, the p-value, 0.0425.
Yep. If I added one thing to the model and that one thing is significant, that means the R-square change is significant. It's a one-to-one correspondence. Now we get to do interpretation time. So intercept, my beta 0, that's cognition. That's predicted for an 85-year-old with grip 9 man without dementia. These are the marginal main effects of gender and dementia. So it looks like women are significantly lower than men. People who are going to get dementia or have it already are significantly lower than those who don't. And all of that is irrespective of age and grip. Okay, so we'll just ignore those for right now. Now this age slope right here, what does that mean? It's simple or conditional. So all slope sentences start out the same, right? The slope is the expected change in y for unit change in x. So let's put that into the story. For every additional unit x, for every additional, what's x? age, year of age. So for every additional year of age, predicted cognition goes up or down? Down by 0.33. When, yes, the conditional part, keep talking. When grip equals 9, because of the interaction. The only time in which this is the only part that goes into the effective age is when this is 0 and that thing drops out. So the effective age is given by beta 1 plus grip times the interaction. So it's only beta 1 if grip drops out, and grip goes to 0 when it's 9 based on my centering. Now, which pattern is this? If I have a grip of 10 instead of 9, this is a less negative. So the effective age in people with grip of 9 is minus 0.3. It becomes less negative by 0.12 per what?
Grip.
Per age grip, exactly. I'll say that again. The age slope is minus 0.3 for people who have a grip of 9. That age slope becomes less negative by 0.12 per unit grip, the interacting variable, the moderator. So less negative, let's put that into English, because reviewer of 3 ain't having it.
Subsides.
I like that one. It weakens, right? Less negative means it's moving towards 0, so it's weaker, it subsides, its grip is a protective factor, we can do that one. Aging doesn't suck as much if you're strong. How's that? Or so I hear.
So this might be a dumb question, but when we do the grip part, so now is the grip conditional, or maybe you're going there, is the grip conditional on the age?
Yep.
Okay, since we times them together, it's not a unilateral relationship.
Yes, it's both. Yep, and that was exactly where I was going next. If I start here, this is, okay, slope, change in y per unit change x. Okay, so for every unit x, what's my unit x? Pound squeezed. Predicted cognition goes up or down? Up by 0.6 in people who are 85. So if I'm 86, what's my age slope, or excuse me, what's my grip slope going to be? Which one is this?
More positive.
More positive. So my grip slope is 0.6 if I'm 85. For every year older, my grip slope is more positive by 0.12. For every year older, my grip slope is more positive by 0.12. So the effective grip is enhanced in older people, stronger in older people. So here are the estimates for the simple slopes. So the age slope that is directly given by the model is that one right there. So for people who have sort of medium strength levels, the effective age is significantly negative. The interaction made it less negative. So as grip increases, for instance, if it's 12, that slope is less negative and actually non-significant. So somewhere between 9 and 12, age stops mattering significantly. You can also go the other way. The slope becomes more negative as grip decreases. And what will eventually happen according to the model? Like if I had grip equals 24, what will this number keep doing? Up, more positive. Eventually, the model says that age is going to have a positive slope if you follow grip out long enough. Now, whether or not there's anybody in the sample that can squeeze 24 pounds is a different question. But the model, that's what it predicts. Okay. Likewise, this is the grip slope given by the model directly at age 85. We said it becomes more positive as age increases, so that's that one. But that also means it becomes less positive as age decreases, and there's that one. That's non-significant. So somewhere between age 85 and 80, grip stops mattering. So the next step that we'll do next time is to find the regions of significance to zero in on exactly when these slopes sort of turn on and turn off and change directions according to the model. As well as pictures, because reviewer 3 can't handle less negative and more negative, but they can stare at a picture. And I made this in Excel because I like making pictures in Excel. All right. And this is in the book too. So. All right. Questions before we adjourn? We'll go back over this again next time. I will see you Thursday. I will let you know when the next handout is ready for the other lecture too. It's not quite done, but I hope to finish it soon. So, all righty. Question?